Thanks, Dave.
Right.
You know, when I came, Dave says, okay, I want to hear about Z14 and pervasive encryption. I said, okay. And then I said, okay, well, is anybody going to be here who knows what a Z14 is? So I have some intro stuff here, but I'm going to fly through it because I'm looking out over here. I know many of you know what a mainframe is and know what a Z14 is. But more important to the, and I have some pretty cool slides that I'm going to fly through that I thought were very intriguing. I stole them from a friend of mine because it kind of, in one place, talked about this evolution of this box called the mainframe. But the other piece that's very intriguing to me is the whole idea of security. So for those of you who don't know, I did my time in the box as the president of CMG. And one of the big things that I wanted to do was, and I have this thinking, so I'm gonna put it out there. I'm gonna divert for a second because I never do that. But I have this theory about CMG, and so right now CMG is, this is my advertising for headquarters. CMG was created back in like 1975. It came out of this B-bug. It came out, the mainframe was just invented. It had just come into a virtual world, and there was this gap. I'm going to call it the gap. This is not the gap that you mind when you're in London, or this is not the gap that you put on your spark plugs. This was the gap in knowledge. This was the gap in how do I do things? How do I measure this thing? There was all sorts of things. So a group of people got together and created a synergy and created this vision of how do I move forward and how do I measure this beast that costs a fortune. People think it costs a fortune. Now you're going to see a little bit relative here. It cost a fortune. It did very important work. It still does very important work. And I needed how did I optimize those resources, and how do I make it work and get the most out of my investment here? And without instrumentation, without any kind of knowledge, I had no freaking clue how this thing worked in the background underneath the covers. You had to be a wizard, like my man Chuck here, who figured this out. But CMGers got together, forced instrumentation, inferred how things, what behavior was occurring with the mainframe based upon stuff, and created this synergy that created this whole discipline of performance and capacity management. So my challenge to you is, right now, CMG, we spend a lot of time doing what I call looking in the back view mirror. We talk about what we did. We talk about how we did it. And we're pretty proud of it, and it's a good thing for people who had not been part of that journey through the forward here. But we talk about the back view mirror, and we train people that hadn't done stuff before we do all this stuff. But I want to go back to 1975. I want to go back where we're looking through the front windshield. I don't know where I'm going. There's a lot of stuff I don't know, that I don't know what I don't know, and I have to figure out how to do it. So I'm going to challenge you. You can come up and talk to me later or whatever. What's the gap today? What's today's gap? How do I transform CMG to deal with the gap of the 21st century? Because it's not about instrumentation of the mainframe. Guarantee it's not that. So anyway, as part of this process, what we were talking about is that there's some imperatives that have been come forward in IT these days. Y'all have seen them. They're the CNN moments. This is where you get to be on the news about how 70 billion of your records got pinched, and somebody is selling them on Amazon, dark web Amazon, and you can buy your information. You can buy your financial information. You can buy access to your accounts. You can buy access to your credit cards. You can do evil things, which is the whole crypto ransomware discussion. This is right now, ransomware is all about money, But there is an evil side that could be coming to this, because the idea of what can be hacked and encrypted, it's not just your computer. It could be your car, it could be your pacemaker, it could be a lot of things. And so when you have this level of ransom, consequences get much higher. And the idea of how I'm going to deal with the security. The other piece of it is that, and you're going to hear about it later today when Chris Greco talks about the intersection of performance capacity and cybersecurity, because what you're going to find is that they're very similar. There's similar skills applied a little differently. It's pattern recognition. It's identifying things that are going on and trying to determine them. It's an opportunity for a different, interesting career in IT. So how does that relate back to what is the Z14 here? So what I'm going to talk about a few things, because I'm going to talk about a few things, and I'm going to talk about some of them fast and some of them a little slower. And if you have any questions or whatever, let's just take them at the point. And I can guarantee you that I'm not going to be down 14 points to the right of the decimal point of the detail about this discussion, because it could actually go as much as you want it to go, and it can go forever. I know people in IBM who can talk about this pervasive encryption. One slide can talk about it for 2 hours. So there's a whole lot of stuff, but I'm going to talk about some of the things that went into why IBM worked for the Z14. This digital transformation. This is where I stole the slides, and so you might like them. I'm going to do a little bit of an overview of the Z14. I'm not going to cover every single thing that went on that's in the Z14, but I'm going to cover this, the basic construct, the basic things that are part of it, and how that relates to pervasive encryption. So this is kind of a little bit lead in here, is that I know that everybody claim, there's a lot of belief that the mainframe is a dead box. It's not anywhere. But the other side of it is that what I like to think about is that your life runs on this mainframe. You fly on an airplane, your ticket came from it. Most of the time, if you bank, your money is being protected by this box. There's lots of places where it works here. And billions and billions of transactions a day run on this box. It runs in the background. It doesn't stop. And there's an expectation, in some respect, it's sort of like your electrical power or your telephone. You expect it to be there. If it's not there, it's a very painful kind of thing. So because of that, it's important for this box to have a requirement for integrity in what it does. So IBM, the evolution of this has basically moved this, that there were 3 major imperatives that where does this box need to live? It needs to live in the cloud. It needs to be able to be open and connected to be able to be part of the cloud work. This is sort of like, if you think about it, everyone talks about, do a little corollary here. This is Rick's opinion, this is not the party line, that AI, artificial intelligence, actually, I like to think about it as in terms of its assisted intelligence. It assists you in terms of doing some things that you maybe do it faster, do it easier, do whatever. Think about this mainframe in this cloud environment. It's not the replacement for the cloud. It's a component of it. It assists in this area. I need to be able to, back to this AI kind of discussion, I need to be able to get insights quicker, because if I'm going to be running lots of the information in the planet, I have to be able to, I have that data. Well, why would I want to go replicating and moving things and then process it again? Why don't I just catch it in line? This is all about speed to value. How am I going to get to it? So it's important to have faster and smarter insights. And lastly, then, this was the key thing, which ties back to this security discussion, that I have to protect your data. So I will become the royal we of IBM. You entrust us with your data. You entrust us with your information. We have a responsibility to protect that information as best we can, to protect you from yourself, to protect you from evil people, to protect you from accidents. That's part of one of these design points of the mainframe, is to create this idea of a trusted experience. And these are some, everybody thinks that protection of your data is just encrypt. Yeah, you encrypt it, it's all good. Well, that's the counter to it's encrypted and it's good is that I have the key to my data. The idea to encrypt it and it's not so good is when the other guy has the key to my data. So the idea here is that it's important. But what's interesting is, and I've always found this to be fascinating, is that all these data records being stolen and everything, since 2013, of the 9 billion records that have been stolen, only 4% were encrypted. That's fascinating when you think about how much everyone needs to and focuses on encryption here. And why is that? It's because most companies do selective encryption. You encrypt the PIN number, but you don't encrypt all the data. You don't encrypt your birth date. You don't encrypt, there's a lot of stuff that's not encrypted here. And why is the reason for that? Why is it I only do a little bit? It's because this stuff's hard. It's not easy. There are considerations that come to play whenever I start encrypting all my data and what I'm going to do. But you know what the bottom line here is, that even though it's hard, you're going to have to do it. So So think about it like this, and this is one of the underlying things about IBM's pervasive encryption on the mainframe here. What if you could encrypt everything without changing anything? What if I could just put an umbrella up and keep the rain off? That's what I'm basically talking about doing with pervasive encryption here. And that's what I'm going to show you, the first step in this idea of encrypting things. This is not the end game of pervasive encryption. This is the first step of what was announced and released here. And the bottom line here is that IBM believes that trust was the most important valuable thing. Why is Bitcoin worth $12,000 a Bitcoin? Well, part of it is because if you have one, you trust that you have it. So anyway, this is a little bit, I'm going to kind of talk a little bit about how did this mainframe, something that was created really back in the 60s, but went virtual in the 70s, and how it evolved here. And I'm just going to kind of go through this, and you're going to get a feel for the journey the mainframe has been through, and the idea that it's not what you thought it was before, because this is what you thought it was before. This is what it was. Looking back in the back view mirror, I look back to 1975, and I look back to the points in time where I was. What was the mainframe? It was KICS, it was IMS, and it was JES, whether 2 or 3. And I did transactions and batch. And then all of a sudden I had this idea that I'm going to do this application development, and I'm going to have this life cycle, and I'm going to do this. So I'm going to add in some languages, COBOL, and I'm going to add TSO and ISPF, and I'm going to do waterfall development. And then all of a sudden I'm going to start to do some integration of the application, the operational data, and I'm going to add in some more stuff. I'm going to add in databases, and I'm going to add in file management, and I'm going to add in, and I'm all of a sudden going to be working with this idea of how do I integrate it, and I'm looking for patterns, and I'm going to have operational data and this idea, I'm going to do this. And then all of a sudden, wow, I have all this data, this whole focus that went on for the idea that I'm going to improve my business cycle. And you see, I'm starting to add up. There's all this other stuff that's all of a sudden started appearing, and going across the top, I have a whole bunch of new, it's not just, IBM DB2, and it's not just, there's all sorts of things going on. And all of a sudden now I'm in this idea that I have this connected world. I can run the planet. I have more compute power in my pocket than they went to the moon on. Apollo 13 would not have a problem if they'd had an iPhone. They wouldn't be going like this to get themselves back. They would be able to just plug it into the calculator here. But all of a sudden, I'm connecting into everything, and all of a sudden, I got to tie into the internet, and it's not just captive, and I'm working these things. And all of a sudden, I have this Internet of Things and this real world data, and now I'm tying all this. All of a sudden, you see, I have this API, this thing called APIs, and I have mobile development, and I have REST, and I have JSON, and I have connecting, and I'm running Java. I'm running all this on the mainframe too. It's not just running on your PC. And then I have this stepping through. I'm going to modernize my applications, whether I'm going to wrapper the existing applications or I'm going to replace them. And all of a sudden, I'm going to be playing with Java, and I'm going to be start doing these APIs and what have you. And then I start thinking about, well, this system of record that I have is very important, and there's a whole lot more new languages that are coming up to play. And I'm starting to add all this stuff. You notice that this mainframe is not just a single box anymore. There's lots of bits, lots of things. And I know all of you have experienced and stepped into this journey one way or another, at one point or another, and you see all the legacy that came with it. Legacy is not necessarily a bad word. Legacy is a good thing, because I can build upon this legacy, and what I can do. So now I've stepped this up, and I'm going to say, wow, I have all this data, and I have new capabilities, the abilities to infer something from this data, this idea that I can get insight from the stuff that I have. And this has all started to add on, and you see now I'm running Python, and I'm running R, and I'm doing all this magic. And now I'm starting to score and do predictive analytics. I'm going to do machine learning, because I'm not going to cover this, but I'll tell you one thing. One of the big announcements in the Z14 was the support for machine learning. I can do actual machine learning and AI on the mainframe today. I don't have to run it on a specialized processor. I don't have to run it on GPUs. At the bottom, there's a continuum of this work that I can do. Then I'm going to add in this idea that I'm going to do it in the cloud, and I'm going to do it self-service, and I'm going to have automated provisioning, and I'm going to standardize, and I'm going to be able to expand and contract and do the things and things. And I'm going to add on more. Look at all the pieces across the top and on the sides. This all runs on the mainframe. And now I'm going to deliver it on the cloud. And what this all really comes down to is the idea that this one box has evolved over the last 50 years to provide that systems of record function, that idea of being able to get insight from the data, the idea of being able to engage with whoever, whenever, wherever it need to be, to reach out and to provide that information as systems of IT. So anyway, I always liked this because it was very interesting to me. I could bounce through this and say, oh, I remember that. That's pretty cool. So I'm going to talk a little bit about the Z14. So I got to make sure that I don't steal it. This box was announced on July 17th. It was generally available in September of this year. It's funny when I think about that the Z10 is an N-4 box. I remember the very first box when I first started with IBM. I started out with IBM on the same day that the 3380 and the 3081 was announced. And boy, was that hot stuff with MVSXA and 31-bit addressing and dynamic path reconnect and 16 MIPS. Woo, we were cooking with gas. This is an interesting thing because this is a little bit about the Z14, but it's only going back to the Z900. It's only going back 17 years. And so these numbers that you see across the top, 6.1B, what that is, that's 6.1 billion transistors on a chip. This is the evolution of the transistors. This is the evolution of how many cores on a chip. This is the evolution of the blue one is an interesting one because, when if you think about that evolution and all those things that I told you that the mainframe can now do, and how does it get that capability to doing that? The blue ones here are the number of new instructions that were added to the chips to handle things like garbage collection, to handle things like doing better mathematical processing. This every time, because what you're going to find is that there is, you notice that, you know, everybody likes to say they have the fastest, you know, horse on the block, but the mainframe has been pretty much up there, as long as you don't start overclocking, that the mainframe has been up there at the fastest gigahertz speed. And the mainframe has been delivering 10 to 15% performance improvement every generation. But at the same time, the mainframe has not been speeding up the clock. And so how does it get that performance improvement? It gets it through all those pieces that were added on, gets it through that instructions, changing these, gets it the performance from adding other capabilities to it. And so another thing that's interesting, so remember, you know, granted, I let you know when I started, the 3081D 16 MIPS, that was a pretty expensive box. That was 16 MIPS, but that was 16 MIPS off of 2 cores, 2 processors. That were 8 MIPS apiece. The Z14 is 2,000 MIPS on a single core. Just a flesh wound. So how did I make this happen? What did I do with those 6 billion transistors here? So this is a comparison. This, what did we do with the transistors? This is what we did with the transistors, which is how we got that performance improvement for you. We spent it. We added 2 more cores to the chip. So now instead of 8 cores on a chip, there's 10. We added more level 1 cache, added more level 2 cache, added a level 3 chip cache, added new instructions and circuits, 400% more transistors in the encryption, which is important for pervasive encryption because while encryption is hard, it's also expensive depending on where you do it. We added some SIMD registers and circuits. There was new protection and circuits, new compression. All these things is where did those 2 billion transistors go? They went into these things. Yeah, we changed the surface area from 22 nanometer to 14 nanometer. And if you think about it, you can only do it in terms of shrinking the size. Well, once you get to 1 atom separating the circuit, it doesn't get any smaller. And the reality is that if you have it only that much separation, you have so much seepage, it won't work anyway. Another thing that we did on this is that the idea that, excuse me, that we're going to do more things with this. All those things I talked about at the very end. I'm going to play with cloud. I'm going to do AI. I'm going to do all this stuff. Well, you know, memory is important. In fact, what was it I always said that, you know, the cheapest upgrade you could ever do is adding more memory to your laptop, to your mainframe, whatever. Add more memory, it'll be like you have a whole new machine because the memory is important. Now, what do? We changed it from a max of 10 terabytes to a max of 32 terabytes. That's a lot of memory. That's a whole bunch of memory. Now, this RAIM thing, because you know the idea that I'm going to protect your information, I'm going to protect your data. RAIM stands for redundant array of independent memory. Basically, going back from the EC12, we basically have created a RAID array within your memory. So if I lose a single chip, I'm not going to lose. I'm not going to say never. There's always some black swan event that occurs, but the idea here is if I lose a chip, I don't have to reboot, I don't have to re-IPL, I don't have to do stuff. So what do we do with the extra memory? Well, now all of a sudden I can do more data in memory. And and I don't know if anyone has worked with these. Back in the 13, we had this Flash Express. So we had a Rocky channel where you could put a flash card and you could use it for, for a dump data set or what have you. We got rid of it. Because we have the memory now, basically the Flash Express is now being carved out of memory. Yeah. Sure, absolutely.
Does RAID work the same way as RAID does in storage?
Yeah.
In memory instead of on drives?
Yes. Sorry, what was the last bit?
Just on memory instead of on drives, does it work the same way as RAID does on storage arrays?
So the question was, does the RAID memory act similar to the way that storage does? The answer is yes, but it's obviously not exactly the same. But yes, it's basically there's a rotating parity going across chips. There's not just a parity, just the same as disk. Remember when first disk came out, there was the parity disk and then there was the rest. And then they said, well, this is really stupid. We're going to spread this out so it's rotated across, spread across, so you don't have to lose any one. You lose one, or you don't have a massive. But yes, it's a similar construct.
So this is different than chip kill.
Yes. Yes. The question was this different than chip kill? Yes. Chip kill is about, well, obviously there's error correction code that's involved in it to try to recover a mistake or whatnot. If I can't recover a chip or what have you, yeah, the chip kill is then I mark it invalid. I basically dump it. Long time ago, we had a whole bunch of boatload of extra chips so that you still had, then it would be brought back on and worked. And obviously they work together in terms of if there's a major failure and what have you to protect it. Because there would be times that if I had something in memory fail, that then I could have to reboot because I've lost something important. With RAID, I mark it bad. I bring in a replacement for it, whether it's a full chip or just a cell. If it's a full chip, then it'll be marked off, marked bad. One of the spares would be brought in, taken its place, depending upon a threshold whether or not it would call for a repair action to replace it.
Okay, so does this work across memory controllers to keep this? Or is it just within a DRAM or a pair of DRAMs?
So the question is that does it work? Does RAID span memory controllers, or is it just within a single bank of memory? The answer to that is that it's the central memory. Think about it as that the RAID is all the central memory, up to 32 terabytes of central memory, and that's all RAID and controlled, and obviously there's multiple memory controllers and what have you. It's not RAID inside of a memory controller or some, embedded device of some sort, so it's not that. Anything else? Okay.
Memory access latency. How do you actually get 32 terabytes worth of addressability and not have latency problems?
Well, okay, so the question is, how do I design a memory subsystem to not have to fetch from one corner of the memory environment to the other corner of it, and do I make shorter? So the idea of how do I manage the latency within a large memory array? The answer is yes, it's a challenge. Yes, there are algorithms for positioning. You like to keep the memory that you're using for your address space, you like to keep it adjacent to the cores that are processing your work. And so there's been algorithms and part of the operating system to do that.
To enforce clustering.
It enforces the comment was that does it enforce clustering? It's not necessarily clustering. It's about adjacency to optimize the processing. Does that make sense? I don't know all the ins and outs of how they do in the
That's
algorithms.
basic intent.
The intent is to not have to make a long reach. The intent is not have, and I have a picture later of the nest, which is multiple drawers. The idea here is not to have to be processing on drawer 1 and its memory is in drawer 4, because yeah, I have to send signals down to get to it. Can I do it? Yes. Will it, if it happens to occur that way, will it strive to probably move it up closer to the processing? Yes.
I have a question.
Yeah.
Yeah, from what I understand, at the Z14 level, I don't know if it's Prism, but somewhere down deep in the bowels, it will actually relocate memory behind the scenes to get closer to the processors that are doing the work.
So the question was, is this Prism or other, is there a function within the box that tries to position that memory? And the answer is yes. How it does it, I have no clue.
So good question. Well, so it's evidently dynamic, where it happens all the time. And I don't think there's any indication given to a performance guide that it's happening.
So the question is that it's happening all the time, it's dynamic, and is there a report that this has occurred? I don't know. I don't know if there's a report that it's occurred. I can guarantee you that that's not supposed to be a general happening all the time. That's more a correct because I had to do something because of the workload dynamics at the time allocated this, and that was the free space or what have you. It's not, this is not like to be like, let's page stuff out, let's page it back in and resettle it and stuff. It's more the exception, but you know, when you've got so many things going on that you could get to that point. And it'll be more true for a long-running started tasks that take up residency and stay and run forever versus my batch job that runs, runs for, it's got three minutes of CPU time and it runs for an hour and a half. It's not going to, I don't think that that's the key thing. This is a picture of what, so one of the things that has always been true for mainframes is that it runs a single thread. It's an SMT, symmetric multi-threading, SMT1. It's always been that way, 2000 MIPS, 5 gigahertz. This is a picture of what, and this is a picture of an architectural picture of what one core looks like. What we came up with in terms of Z14 is now, y'all that have been working with Z for a while and everything know that there are specialized engines. Well, engines that run specialized functions, zips, zaps, SAP, system assist processors for IO, different ones. What we did is that, and engines that are running Linux workload in an LPAR and what have you. What we did is that in the Z13, we enabled SMT2 for IFLs, for running Linux workload. In the Z14, we've added the SMT2 to everything but the general purpose processor. So everything that's not running, that's running anything other than ZOS or running in the general purpose processor. So zips, zaps, or that function, SAP, they basically can run SMT2. And what get out of that is that I start to take up some white space and I get an effectiveness of actually bumping up the amount of MIPS that I could get out of one of these cores. This is a growth. On that real estate, back to your latency question, Dave, the idea of where do I put this? I only have a certain amount of latency of real estate, so how do I position these things to minimize even the time in between these? So this is just the layout of what it looks like here. Now I take that picture that I showed before, and now I put it all onto, this is one process, this is one processor, 10 cores. Each of those cores is on the core. And so what did I do with the cache? I put the cache in the middle because the cache is being used by everybody. So I have an equal path to get to the cache. I increased the amount of cache. I got 10 cores. And then I take all of those and I put them into a drawer. This is the building block of this. I'm going to create a drawer with 1, 2, 3, 4, 5, up to 6 of these building blocks, 10 cores. And I'm going to put memory on it. I'm going to put a storage controller. I'm going to have PCIe 3. How I'm going to do that? That's the drawer. And then what do? I create a nest. I take up to 4 of these drawers, from the smallest to the biggest Z14. So I can go from 280 MIPS to 150,000 MIPS in one of those sub-zero refrigerator size operations. A double door. I got lots of meat in here. I got lots of vegetables and what have you. And I can put 150,000 MIPS in this box. I don't know anybody that has one of these 150,000 MIPS. I didn't know anybody who has the largest amount for Z13, but I know they exist. I know there are customers of IBM who have multiple of these 150,000 MIP boxes. It's just incredulous to me when I think back to the 3081D. So I'm going to throw in here what we also did with the Z14, so that underlying infrastructure that I talked about here, there's a separate box that only runs Linux, and it's called the Linux One. It has the same building blocks, it has the same capabilities and what have you, but it's a Linux only box. So with that as background, and how much time do I have, Dave? Okay, good. Now I'm going to talk about pervasive encryption. So why did I do that? The bottom line here is that it's not if but when. I can't even tell you how scary this this whole problem with cybersecurity is here. 28% likelihood you're going to have a data breach here. The bottom line here on this, only 2% of the corporate data is encrypted versus 82% of mobile device data. Everybody encrypts their iPhone or their Android phone. It's all encrypted. The FBI hates it. But everybody encrypts their laptops, but the corporate data is not always encrypted here. So what we tried to do here is with the pervasive encryption is to create this idea that I can protect in-flight and at-rest data without having to spend a whole lot of massive effort and time. There's lots of regulatory.
Can you just dwell on that whole point of data at rest and data in motion?
Yeah.
Because those are two really different things.
Yep.
And one of them is really hard. So
yep. They're all really hard, and I'm going to talk about it because I have some example use cases of both of where pervasive encryption 1.0 is working right now. There will be a pervasive encryption 1.1, 1.2, 1.3. We're not done with this, but there's lots of all those breaches and all those people that got stolen and stuff. Basically, it's the idea that do you trust all your information to some company in California? Do you expect them to protect that information? Do you do it? Well, there's legislation now that says, yeah, you will protect it. You will tell me if you get breached. You will do all this, or I'm going to make you pay. And the latest one that I'm going to make you pay is this GDPR. It's a European regulation here that puts massive amounts of consequences for corporate bad behavior and for not taking care of your data. And yes, it's a European standard, but it impacts any company who does business in Europe. Got to apply to this. And the consequence is percentage of your profits worldwide. It's a big deal. It's a big deal. And so if any of you all are working in, are hearing about there's a big push to get encryption in place for everything at rest and whatever, I can guarantee you that every corporate entity that I deal with, GDPR is a big deal. And GDPR goes into effect the middle of next year. So what did we do with pervasive encryption here? We designed this thing for pervasive encryption. So remember I talked about the 400% more chips. I'm going to use some of that real estate on transistors for the encryption. That was the CPAC. I added more capabilities and performance into the ability of the Z14 to do encryption and performance. So there's a new Crypto Express. There's a new way for handling keys of the thing. I took a new approach in terms of ZOS. Pervasive encryption, I'll just tell you right up front here, pervasive encryption right now, everything, and most of the stuff I'm going to talk about, it's all about ZOS and protecting the data here. There is a capability to apply these exact same structures for Linux on Z. So if I'm running Linux and I'm running I'm running stuff, there's a capabilities of it, but there are things that you have to do to make it be policy driven and auto magic, and that requires some things. And so if you go to Linux land, that requires some things need to be in the kernel, need to be in the distributions and what have you. So think about it like this. I always love this because to me it makes all the sense in the world in terms of this idea of how I can handle encryption and how do I have multiple layers. So what did I start with? I started with full disk and tape encryption. Why did I start with that? What does it protect against? It protects against somebody stealing that tape cartridge. It protects against me dropping the tape cartridge off the back of a truck. It protects me from someone going into my environment and rolling out a disk array, because you know I'm running RAID and so it's not in one disk, but it protects me for those things. It definitely protects my laptop because it's all on one, but it protects physical intrusion and tampering of the infrastructure. But once I go above that, this is where it gets harder. So the next level up here that we think about in terms of this idea is taking on files or data sets, then taking on databases in terms of from a certain part of the database. And the hardest part to do is when I go to the application and protect specific things. And why is that important here? Because there are because if I think about this, I talked about this in terms of full disk and tape. It's all or nothing. Only the data at rest is encrypted. There's one encryption key for everything. It's basically doesn't cost the CPU, doesn't cost any kind of overhead to the host because it's all done off board. But and I think that's important, this idea that there's one encryption key for everything, because if I only have one encryption key for everything, that means if I have the key, I have everything that's on there. It doesn't matter that I might want to have some role basing, I might want to have some need to know, I might want to have, but it protects against something disappearing or leaving the building. It's a physical level stuff. Yeah. Yep.
So can you explain the zero host CPU process? Is that based on that the encryption is being done on these auxiliary ports? So,
no,
what I'm being charged for on my host processors is not including encryption altogether?
No, it means that the encryption is actually being done at the disk drive or the tape drive. The drive itself is doing the encryption. It's a single encryption kind of thing. This is not like I'm running. So this is not the same as running PGP on your Windows machine or running Firewall on Apple machine, where it's taking general purpose cycles off of your.
Encrypted out of the device.
Yeah.
It's got its own encryption.
how's the service time changed?
Doesn't.
No.
How does so the question was around the idea of the disk. Where does the encryption occur, and where does it? And in terms of the overhead cost of where does it do? So is that any?
Yeah.
We good? All right, cool. So this is now we're going to step into where we're playing in terms of pervasive encryption. And pervasive encryption is, while it plays at all the next three levels of the pyramids, it basically focuses on ZOS datasets today and database. And here's the key things that are important about this. It's transparent to your applications. I don't have to crack open any application and write any code inside of a program to call some encryption or to encrypt this thing. I basically run it based on policy, SMS policy, RACF policy. It's all related to the access control, and there's a whole key management requirement. It has to be in place. I have to have a key manager. I have to have, you might have rotating keys, you might have keys for different functions and what have you, but I have a key management and stuff. I basically encrypt everything. It covers the vSAM, DB2, middleware logs, everything today. It takes advantage of that hardware on the Z14. It also can run on the Z13. It doesn't run, it's not as efficient because of those enhancements I made to the cryptography on the Z14. And I have, because I know this is CMG, if we make it to the end, I have some performance data for you too. So this is a little bit more in terms of the scope of that protection. I basically protect the access to the data. I separate the cryptography between environments. I can protect your data remotely, your DR. I can protect backup and migrated data. I can do all of this stuff. So how do I move up the food chain a little bit to the database? And so now I start to bring in, it's not all one product that takes care of this. So this, in terms of using for DB2 and IMS, I have Guardium data encryption to take care of this. This gets into some separation of duties. It can give you the ability to go within DB2. Now DB2 has always had this function where you can do selective encryption. The problem why a lot of people didn't use it widespread or its selective use, it takes general purpose MIPS to do it. And so I would use it for PIN data, I would use it for maybe passwords, what have you, but I wouldn't do bulk encryption of everything. This gives me the capability of using that functions to handle the databases. And lastly, this is the one that's the hardest to do. You got to crack open the application. You got to go into the logic of the application. You got to decide what pieces you're going to do, and this takes time. And you know, GDPR is not waiting for you. And the idea that and then as soon as I do that, now I've added this to my maintenance cycle. Isn't it always easier to have it just take care of it for you, and you never have to change the application? You focus on changes to the application based upon function and things that you want to do, versus I now have a whole cryptography level that I need to deal with inside the application. So,
What kind of impact does it have on application performance?
sorry?
What kind of impact does it have on application performance?
So the question is, what kind of impact is there to the application performance? You're talking about pervasive or doing it, opening it, the application up and changing it? It can be pretty massive. It can, depending upon, if you open it up and there are software products out there that enable you to do these things and to open it up and to add it in. They do the encryption in stream and the general purpose. They can add 20, 30, 40%. That's why And then the same thing would be true if you ran DB2 using, you know, row level or field level encryption. That was all general purpose. And that's why people only do a little bit here, a little bit there, because it took MIPS, it costs money. It costs money on software because it drives up your utilization. As far as an individual transaction, it would depend. I don't know the answer to that. But I do know the answer to the overall measurements for pervasive encryption. And if you remember when LPAR first came out, now see, I'm dating myself again, but LPAR first came out and it was 10% overhead. And then it became 5% overhead. And then it became a rounding error. And now it's just standard. You expect to have that virtualization because it's 1.5 percentage just cost to do a business for the function. Pervasive is not coming in at 10%. It's coming in at the lower already because of the offload that's going on in terms of the encryption. And I'll have that show you. So this is just basic, yeah.
One more question. So what's managing the keys for all this encryption? And how does that work when you're either replicating data to another device or moving encrypted transactions between devices?
One of the requirements for pervasive is to have a key manager. Oh, the question is who's managing the keys? Yes, there has to be a key manager. IBM has a key manager that you can use. There are other key managers that, and lots of people don't all use the IBM key manager even today for whatever, for the encryption that they're doing. You have to have a key manager, and that gets into, if you have the key manager in place, then it allows you to do rotating keys and do, you know, who has authorization and stuff, but you have to have a key manager. And obviously the remote site, you know, you can handle it one of two ways. If I need to recover in the remote site, they need to have the key. So the keys need to be synced up through the key manager. This is the data set encryption here. So I'm using the encryption capabilities. I'm using, and you see the orange here, this is what's encrypted. So it gets encrypted before it leaves the host. So then it's being stored encrypted. Now you could have turned on data set encryption on the devices. 5 minutes. All right, I'm gonna have to be quicker. That's what happens when I ramble. You can turn on, you know, do device encryption and stuff. It doesn't matter, but the whole key and everything you're doing here is handled through the RACF, through the data set. It goes out encrypted, and the management's back up there. If you're running parallel sysplex, personally, I don't think that this, to me, it's not a big deal. I don't know anybody who's sniffing the coupling links, but the capability exists underneath this there to basically encrypt everything in the coupling facility and everything coming from the members. Network, I could do the exact same thing using this pervasive encryption if I'm using, you know, the IBM COM server, then I basically have the exact same capability to encrypt it out across the network through pervasive encryption. This is the piece that's part of the Linux on Z. There's a function here called secure service container, where I basically have a hardened secure environment. This is the environment that you think about using this if you were standing up a blockchain instance, if you're going to have a consensus in blockchain. This is all IBM uses this for our high-speed business network for blockchain. We use this for database services. You could put a database and harden it and what have you in here. Use cases. I'm going to probably blow by this. Today, what can I do? I can encrypt all the data within a core business application. I can protect any kind of binary large objects. I can protect transaction logs, which is important. And everyone thinks I've encrypted the databases. Well, what about those transaction logs? Because there's actually data in there too, isn't there? I can, through this policy-based kind of feed thing, I can protect the threats from within, because now I'm starting to more enforce. Big deal, that audit compliance. Because if you're not getting audited today, you will be. And the whole security and how you're protecting our data is key in every boardroom on the planet.
So, question.
You said I only had 5 minutes.
I'm gonna take 7 of those 5.
Oh, okay, good.
All right, so, besides I control the clock, so
Oh, you control.
I just hit stop.
I make the
I
rules.
just hit the stop.
I make the rules.
Right. So, given that you guys are taking on a huge amount of responsibility, when these kind of enforcement actions might occur, are you there with your customer at that same table with the enforcement body?
Okay, so Dave is trying to reach into IBM's pocket for any audit that ever occurred. So is IBM at the table guaranteeing? IBM is not guaranteeing things. IBM is not guaranteeing your implementation. IBM is not guaranteeing your practices and procedures, but IBM is providing tools to enable you to enforce your policies and procedures and what have you. There is no warranty guarantee implied or presented that you will never be hacked and you will never be busted, because you have to go back and realize that most of these really good CNN moments start from an internal source of somebody opening a mail or somebody doing something they shouldn't have done. And if you have the authorities and you have the root password, you're an authorized agent.
Equifax, they were behind on maintenance.
Well, maintenance, yeah, that's a whole nother discussion about, you wonder why Apple keeps pushing me and telling me I should update to High Sierra right now. Every day I say, I'll do it tomorrow, because I don't like to be the first person with the new release. All right, some considerations. This is to get into your question about what's it require. I need to have the idea that IBM provides this enhanced data compression function, ZEDC, for compressing. The Crypto Express, the newest one. Part of the Z14 is the trusted key entry workstation, but more important than that is I need to have some capability of key management. This is I need to have these features that are part of the 14. Remember, encrypted data does not compress. You need to compress it up front and then push it. If you push uncompressed data out to as encrypted, you will lose some efficiency on your disk, put it that way. In terms of the data set encryption, DFSMS will compress it first and then encrypt it. They are going to remain encrypted all through its life cycle till you don't do it. And the EDC is a great function to reduce that CPU cost, because even if you're encrypting blanks, it still takes cycles. So isn't it better to compress the blanks out and then only encrypt the data that's required? Here, I'm not going to get into this, but this is functions in terms of keys. Here's a discussion about the idea of the key management. Key management is going to be one of your big deals that you need to integrate, because I guarantee you have a key management going on today. They need to be integrated with the idea of thing. What do I need to do for data set encryption? Choose an application, create a test environment, and then after you've shaken it out, plan for the production. Performance. This is the early testing. There have just been recently some more benchmarks done on this that actually are validating a lot of this early testing. 7 times faster. Obviously, large block sizes are a good deal. The encryption overhead, it's expected to be low, and it's proving out in benchmarks and what have you that this pervasive encryption for OLTP is good. If you're IO intensive, back and forth, encryption, you're going to be doing lots of encrypt, decrypt. This is the interesting one. So a Z13, if I was doing it, the average, these are some early testing that went on, the average was on a Z13 that it would be about 11.5, 12% overhead for doing pervasive encryption. Compare that to the 14 of 3%. 2.5%, 3%. What is that? Why is that way? It's that way because of the Gen 6 encryption card on the 14. It's probably the biggest reason. And then the whole other layout in terms of what it's doing. The good news is we're going to let you figure out what's it going to be for you. So this batch network analyzer, you can download this tool, you can use it, you can process your data out of your SMF data set, and you can basically whether it be a 13 or a 14. Bottom line here is that, you know, you ask why is IBM trying to do this? We think that protecting your data is probably one of the most important things that we can do. And there's a whole other raft of things that circle around protecting your data in terms of security. IBM has an entire whole division that is all about protecting your data, whether it be how do we implement multi-factor authentication to identifying and fixing things. So pervasive encryption is one of those infrastructure as a service capabilities. That's my opinion, is that it's an infrastructure as a service capability of how to make it easier and allow you to implement faster and to not be as costly. It's always about being cost effective. So anyway, did I make it on time, Dave? I'm close. Any more questions? All right, I appreciate your time, and think about the gap, because I really want to have some input.